Between January 12 and 17, 2026, NASA released spectacular images through the Hubble Space Telescope, capturing infant stars in various stages of formation. These stellar baby pictures represent detailed observations of protostars, young stars still gathering mass while hidden behind thick cosmic dust. Stars form when vast gas and dust clouds collapse under gravity. These molecular clouds contain primarily hydrogen and helium with trace heavier elements. When regions become dense enough, gravity overcomes internal pressure and material falls inward. As clouds collapse, they heat up and spin faster, flattening into rotating disks with most mass at the center. This central condensation becomes a protostar. Protostars are hidden from optical telescopes by thick dust envelopes that absorb visible light and re-radiate it at infrared wavelengths. Hubble's Wide Field Camera 3 detects near-infrared emission penetrating thinner dust regions, allowing astronomers to peer into outflow cavities carved by powerful jets and stellar winds. These jets, traveling over 150 kilometers per second, shoot from magnetic poles, carrying away angular momentum and allowing continued mass accumulation. The January 2026 images were part of the SOFIA Massive Star Formation Survey, investigating how stars with more than 8 times our Sun's mass form. These observations provide information about outflow cavity structures, radiation fields, and dust content. Cepheus A. The Cepheus A region, located 2,400 light-years away in constellation Cepheus, is a high-mass star-forming region. This stellar nursery hosts infant stars, including one large, luminous protostar, accounting for roughly half the region's total brightness. Hubble images reveal complex nebulosity. Much remains shrouded in opaque dust, appearing as dark patches, but where stellar winds and jets carved cavities, light breaks through, creating spectacular displays. Pink regions are HII regions, where intense ultraviolet radiation from young, massive stars ionize surrounding hydrogen gas. When electrons recombine with hydrogen nuclei, they emit light at specific wavelengths, particularly hydrogen alpha at 656.3 nanometers, giving characteristic pink-red color. White and blue regions represent reflection nebulae, where light from embedded stars scatters off dust grains less than a micrometer in diameter. These scatter blue light more efficiently than red. The dominant protostar in Cepheus A, with mass already many times our Sun's, provides much illumination. The outflow cavities provide crucial information. By analyzing cavity, structure, size, and brightness distribution, astronomers estimate mass, age, and accretion rate. The radiation field reveals temperature and luminosity of embedded protostars, while dust content indicates how much material was cleared and remains. Understanding massive star formation is crucial because these stars, though rare, play disproportionately important roles. They produce most heavy elements through nucleosynthesis, drive galactic winds, and eventually die as supernovae, seeding the interstellar medium for next-generation stars and planets. Object G03 3.91 plus 00.11. The star-forming region G03 3.91 plus 00.11, designated by galactic coordinates, lies within our Milky Way. The January 2026 Hubble image showcases a beautiful reflection nebula where starlight from a hidden protostar bounces off surrounding gas and dust. Unlike emission nebulae generating their own light, reflection nebulae passively scatter light. The protostar remains completely hidden behind its dusty envelope, detectable only through illuminating surrounding material. The appearance suggests the protostar is in relatively early formation stages, without powerful, well-collimated jets seen in more evolved protostars. The softly glowing nebula indicates gentler interaction between forming star and environment compared to dramatic outflows in other systems. Reflection nebulae provide valuable information about dust properties. The nebula's color depends on the illuminating star's spectrum and dust grain size distribution. By analyzing brightness at different wavelengths, astronomers determine dust composition and size range, providing clues about conditions where planets might eventually form. Studying protostars at different evolutionary stages allows astronomers to piece together the complete sequence of star formation events. Objects like G03 3.91 plus 00.11 represent snapshots of very early formation phases before significant cavity clearing occurred. GAL 305.20 plus 00.21. GAL 305.20 plus 00.21 presents different stellar birth aspects. The bright spot in the center right of the January 2026 Hubble image is an emission nebula, fundamentally different from reflection nebulae. Emission nebulae actively generate light through ionization and recombination. The buried protostar produces intense ultraviolet radiation stripping electrons from hydrogen atoms. When free electrons recombine with hydrogen nuclei, they cascade through various energy levels, emitting photons at specific wavelengths. The characteristic glow comes from multiple emission lines. Hydrogen alpha emission produces red light at 656.7 nanometers. Other lines include hydrogen beta at 486.1 nanometers, oxygen 3 at 495.9 and 500.7 nanometers, and sulfur 2 at 671.7 nanometers. The protostar must be relatively massive and luminous to ionize surroundings, effectively placing it in the high-mass protostar category that will become hot, blue, short-lived stars. Such stars, while rare, dominate spiral galaxy arm appearances and drive much chemical evolution. The complex structure suggests ongoing dynamic processes. The protostar's outflows sculpt surrounding gas, creating cavities and compressed regions. The interaction between outflows and ambient material generates shock fronts where gas heats to thousands of degrees and ionizes by collision. IRIS 20126 plus 4104. Perhaps the most spectacular object in NASA's January 2026 release is IRAS 20126 plus 4104, located 5,300 light-years away in constellation Cygnus. This massive protostar has been extensively studied since its 1983 discovery by the Infrared Astronomical Satellite and represents one of the best understood examples of high-mass star formation. IRAS 20126 plus 4104 is classified as a B-type protostar. B-type stars have surface temperatures between 10,000 and 30,000 Kelvin, compared to our Sun's 5,800 Kelvin. They appear bluish-white and are among the galaxy's most luminous stars. Current estimates suggest IRAS 20126 plus 4104 already has approximately 10 to 15 solar masses and continues accreting material at roughly 1/10,000th of a solar mass per year. The bright, ionized hydrogen region visible at the Hubble Image Center reveals this forming star's power. Jets emerging from magnetic poles plow into surrounding gas at velocities exceeding 100 kilometers per second. Where these jets collide with ambient material, they create shock fronts, heating gas to thousands of degrees, causing bright, glowing, and optical and infrared wavelengths. Ground-based radio telescopes previously mapped IRAS 20126 plus 4104's jet structure in detail. Radio observations penetrate dust, completely blocking optical and infrared light, revealing innermost protostellar system regions. These observations show IRAS 20126 plus 4104 is surrounded by a massive, rotating disk-oriented, roughly edge-on to our sightline. The disk exhibits Keplerian rotation, the same orbital motion governing planets around the Sun, providing strong evidence that even massive stars form through disk-mediated accretion. Discovering Keplerian disks around massive protostars was controversial because some theories suggested massive stars might form through different mechanisms, perhaps by smaller protostar mergers or direct collapse without disk formation. However, observations from Hubble, radio telescopes, and other observatories established that disk accretion is the primary formation mechanism across the entire stellar mass spectrum. The jets from IRAS 20126 plus 4104 extend several light years from the protostar, creating an hourglass-shaped cavity in the surrounding envelope. The cavity walls glow brightly where jets impact surrounding material. By studying outflow structure and kinematics, astronomers probe magnetic field structure near the protostar and understand mechanisms launching and collimating jets. Magnetic fields play crucial roles in star formation, despite being relatively weak by laboratory standards. Interstellar magnetic fields typically measure only a few microgauss, roughly 100,000 times weaker than refrigerator magnets. However, in diffuse molecular cloud gas, these weak fields have profound effects. They provide support against gravitational collapse, facilitate angular momentum transport in protostellar disks, and channel powerful jets and outflows observed in systems like IRAS 20126 plus 4104, the Orion Molecular Cloud. Alongside other observations, NASA's the 14th of January 2026 release included new Hubble images from the Orion Molecular Cloud Complex, located approximately 1,300 light-years away. This is one of the most productive stellar nurseries in our cosmic neighborhood, studied intensively for decades. The Orion Molecular Cloud is visible to the naked eye as the middle star in Orion's sword, hanging below the three belt stars. The January 2026 Hubble observations focused on specific protostars, particularly HOPS 310 and HOPS 181. HOPS stands for the Herschel-Orion Protostar Survey, a comprehensive catalog of forming stars created using data from the European Space Agency's Herschel Space Observatory, which operated from 2009 to 2013. HOPS 310 is almost completely hidden behind dense dust, yet it carved an enormous cavity into its surroundings through powerful outflows and stellar winds. The cavity walls glow brightly in Hubble images, lit by interaction between ejected material and surrounding matter. Bipolar jets of particles, expelled from the protostar's magnetic poles, cut diagonally across the image, showcasing star-forming activity intensity. The outflows from HOPS 310 demonstrate the crucial role of magnetic fields in channeling material and angular momentum. The magnetic field threads through the accretion disk surrounding the protostar, providing the mechanism by which jets are launched and explaining their highly collimated, beam-like appearance. One interesting aspect is the presence of bright foreground star CVSO 188, which appears prominently but is actually unrelated to HOPS 310 itself. This star lies between Earth and HOPS 310 and serves as a useful reference point for measuring positions and motions. HOPS 181 presents a different view of protostellar activity. Near its Hubble Image Center, concealed behind dusty clouds, this protostar sculpts nearby material through outflows. The long, curved arc visible is shaped by material streaming from the protostar, likely from jets shot out at high speeds from magnetic poles. The soft glow pervading the image comes from starlight reflecting off and scattering from dust grains filling the region. This scattered light illuminates dust cloud structure, revealing otherwise invisible details. The 14th of January 2026 release included significant scientific findings from a broader survey of protostellar envelopes. Researchers found no evidence that outflow cavities grow significantly as protostars move through later star formation stages. This was surprising, as many theoretical models predicted cavities would expand progressively as protostars mature and outflows clear more material. This finding has important implications for understanding star formation efficiency. The decreasing mass accretion rate onto protostars over time, combined with generally low star formation rates in cool molecular clouds, cannot be explained simply by progressive envelope clearing. Other mechanisms must be at work, perhaps related to magnetic fields, turbulence, or feedback from stellar winds and radiation pressure. HH80/81. On the 12th of January 2026, NASA released a spectacular Hubble image of HH80/81, a pair of Herbig-Haro objects previously observed by Hubble in 1999. Herbig-Haro objects are bright, glowing regions occurring when jets of ionized gas ejected by newly forming stars collide with slower, previously ejected outflows. HH80/81 is remarkable for several reasons. The outflow stretches over 32 light-years, making it the largest protostellar outflow known. The driving source is a massive protostar, approximately 20 times the Sun's mass, the most massive protostar in the entire L291 molecular cloud. From Hubble data, astronomers measured parts of HH80/81 speed to be over 1,000 kilometers per second, the fastest recorded outflow in both radio and visual wavelengths from a young stellar object. Unusually, HH80/81 is the only Herbig-Haro jet found driven by a young, very massive star rather than a low-mass star. Most HH objects are associated with protostars similar in mass to the Sun or smaller. The fact that even very massive stars can produce well-collimated jets demonstrates that basic jet launching physics operates across the entire stellar mass spectrum. Hubble's wide field camera, 3 sensitivity and resolution, was critical for these observations, allowing astronomers to study fine details, movements, and structural changes. The bright pink and green patches visible in the HH80/81 image result from different emission lines. Pink regions emit strongly in hydrogen alpha, while green regions show strong oxygen 3 emission, indicating variations in ionization state and temperature throughout the outflow. HH80/81 lies 5,500 light-years away in constellation Sagittarius. The extreme velocity and extent demonstrate tremendous energies involved in massive star formation. The kinetic energy carried by these jets must be supplied by the accretion process, as gravitational potential energy from infalling material converts to kinetic energy in jets. Protoplanetary disks. The January 12 to 17, 2026 period also saw release of Hubble images showcasing protoplanetary disks, swirling masses of gas and dust surrounding forming stars from which planets eventually emerge. These observations provide crucial insights into environments where planetary systems form. Hubble observations revealed several edge-on protoplanetary disks visible as dark lanes cutting across light of their central protostars. These edge-on views are particularly valuable because they allow astronomers to measure disk thickness and study vertical structure of material. The dark areas may look like very large disks, but they are actually wider shadows cast by central disks onto surrounding envelopes. One notable disk is HH48, part of a binary protostar system where gravitational tidal forces from the larger star appear to influence the secondary object's disk. This demonstrates how planetary system formation can be affected by companion star presence, potentially explaining some unusual configurations observed in exoplanetary systems. Another interesting object is Tau 042021, a large, symmetrical disk seen edge-on in a late stage of dust evolution. In this system, dust particles clump together into larger grains, a crucial step in planet formation. Initially, dust grains in protoplanetary disks are tiny, less than a micrometer. For planets to form, these grains must grow through many orders of magnitude, eventually becoming kilometer-sized planetesimals and ultimately full-sized planets. The growth process involves several stages. Initially, tiny grains stick together through electrostatic forces, forming larger aggregates. As aggregates grow, they settle toward the disk midplane, creating a denser layer where collisions become more frequent. Eventually, when particles reach roughly meter to kilometer sizes, gravitational interactions become important, and runaway growth can occur, rapidly building planetary cores. The jets visible in many disk images play important roles in disk evolution. By carrying away angular momentum, jets allow material in the disk to spiral inward toward the star, maintaining accretion flow. The jets are channeled by powerful magnetic fields and can reach velocities of 150 kilometers per second or more. Dracula's Chivito. In early January 2026, just before the week-long stellar baby pictures release, NASA announced another remarkable Hubble discovery. The largest protoplanetary disk ever observed, nicknamed Dracula's Civito. This disk surrounds young star IRAS 23077 plus 6707, located roughly 1,000 light-years from Earth, spanning nearly 400 billion miles, approximately 40 times our solar system's diameter, to the outer Kuiper Belt edge. The findings, published in the Astrophysical Journal, revealed that this massive disk is unexpectedly chaotic and turbulent. Hubble images showed wisps of material stretching much farther above and below the disk plane than astronomers have seen in any similar system. Strangely, these extended filaments are only visible on one disk side, while the other side appears to have a sharp edge with no visible filaments. This peculiar, lopsided structure suggests dynamic processes actively shape the disk. Possible explanations include recent dust and gas infall onto the disk, interactions with the surrounding molecular cloud, or gravitational perturbations from unseen companions. The asymmetry challenges existing disk evolution models, which typically assume axial symmetry. The impressive filamentary feature height caught researchers by surprise. In most protoplanetary disks, material remains relatively close to the midplane, confined by the star's gravity. The fact that Dracula's Civito shows material extending so far vertically suggests either the disk is very massive or some process actively lifts material out of the plane. One possibility is the disk undergoes episodic accretion events, where large material amounts suddenly fall onto the system from the surrounding cloud. Such events could heat the disk and drive vertical expansion. Alternatively, the disk might experience gravitational instabilities, creating spiral arms and density waves, which can transport material vertically. Dracula's Civito discovery demonstrates that protoplanetary disks can exhibit far greater diversity than previously recognized. Most disk observations focus on relatively small, well-ordered systems, but this object shows some forming planetary systems begin in much more chaotic environments. The week-long release of stellar baby pictures from January 12 to 17, 2026 showcases Hubble's continuing contributions to our understanding of star formation. From the massive protostar in Cepheus A to the hidden source in G 03.3.91 plus 00.11, from the emission nebula in Gal 305.20 plus 00.21 to the spectacular B-type protostar IRAS 20126 plus 4104, from Orion's molecular cloud protostars to the record-breaking jet of HH 80/81, each image reveals new details about how stars come into being. These observations, combined with discovery of the largest known protoplanetary disk, Dracula's Civito, and detailed studies of planet-forming disks, demonstrate that star and planet formation is a diverse and complex process. The finding that outflow cavities don't expand as previously expected challenges existing models and points toward need for better understanding of physical processes regulating star formation. After more than 35 years in orbit, Hubble continues making groundbreaking discoveries. Its combination of high spatial resolution, sensitivity across optical and near-infrared wavelengths, and location above Earth's atmosphere makes it an irreplaceable tool for studying stellar nurseries. Thank you for watching this scientific overview. Stay curious and subscribe for more real-time discoveries shaping our understanding of the cosmos.